Okay, in this video we're going to talk about another way that we can find the relative maxima and minima, and this is what's called the second derivative test. So what we have is, let's say that we have a graph that looks like this, and it's something like that. Okay, then again here what we have is we have a relative maxima here, and a relative maxima here, and we have a relative minima here. Okay, and what we're going to do is we're going to do the same thing we did last time at first, and we're going to try to find out the places where the slope of the tangent line is 0 or the slope of the tangent line is undefined. Okay, so this here, and this here, if I write these x values, x1, x2, and x3, these are our critical values. And what we have been doing is trying to find what these critical values are, and then we check the sign of the first derivative on both sides and use that to decide if we're at a relative max or min, or whether or not we're at neither of those places. So it turns out that another way that we can check to see if we're at a relative max or min in many cases is by using the second derivative at the critical points. So use second derivative at the critical points. Okay, and so what the second derivative tells you, which we mentioned in a previous video, is it talks about the concavity of a function. So if I have something like this that's opening upwards, I'll say this is concave up. And in this case, the second derivative, f double prime of x, is positive. Okay, and then we might have something like this that's concave down. And here the second derivative is negative. Okay? And basically what we're going to do is we're going to find the critical points, and we can see that, like in a situation like this over here, if we're at a critical point and our graph is concave down at the critical point, then that means we're at a relative maximum. And over here, if we're at a critical point and our graph is concave up, or the second derivative is positive, we're at a relative minimum. So in this case, if f double prime of x is positive at the critical point, then we're at a relative minimum. And if f double prime of x is negative at the critical point, then we're at a relative max. Okay? And so this is what we call the second derivative test. If we check the critical values, we check it's the second derivative, and based on if the second derivative is positive or negative, that tells us we're at a relative max or min. And then we take that critical value and we plug it in to the original f of x to figure out what the y value associated with the relative max and min are. Okay, so it turns out that if f double prime of x equals 0 at the critical point, or the critical value, then the second derivative test is inconclusive, and so that means then we must go back to the first derivative test. All right, so we're going to look at some examples of each of these cases now to see how we would go about actually working this out in a problem. Okay, so let's look at an example of how we would use a second derivative test. So let's say that we have f of x is equal to x cubed plus 3x squared minus 9x minus 13. And we want to use a second derivative test to find the relative extrema. So the first step is going to be to find f prime of x and f double prime of x. And this is going to be just using the power rule to take these derivatives. So I have f prime of x is equal to 3x squared plus 6x minus 9. And then I'm also going to take the second derivative, which is f double prime of x is equal to 6x plus 6. Okay? And so just like with the first derivative test, our next step is going to be to find the critical values. All right, so the critical values are the places where the first derivative is equal to 0, or the first derivative is undefined. Since f prime of x is a polynomial, there's no places where it's undefined, so I can just set it equal to 0. So I'll say 3x squared plus 6x minus 9 equals 0. And then I'm going to solve this by factoring. So the first thing I'll do is I'll pull out a 3. That gives me x squared plus 2x minus 3 equals 0. And then I'm going to divide both sides by 3. And that's x squared plus 2x minus 3 equals 0. And then I can factor this quite easily. This ends up becoming x plus 3 times x minus 1 equals 0. And using this thing called the zero product property, I have x plus 3 equals 0, or x minus 1 equals 0, so x equals minus 3, or x equals 1. So these here are my critical values. Okay, so the next thing that I'm going to do, which I'll do over here, is I'm going to check the sign of f double prime of x at the critical values. So again, what I have is I have f double prime of x equals 6x plus 6. All right, so when at f double prime, if I take f double prime of one of my critical values, which is at x equals 1, then this is going to be 6 times 1 plus 6, which equals 6 plus 6, which equals 12. All right, and this tells me that at x equals 1, my graph is concave up because I have a positive second derivative. So this tells me that I'm at a relative min. And again, I'm going to have to now take this x equals 1 and plug it into f of x to determine what my actual relative min is. And then I'm also going to check f double prime at negative 3. And that's 6 times negative 3 plus 6, which is negative 18 plus 6, which is equal to negative 12. So that means that at negative x equals negative 3, my graph is concave down because the second derivative is negative. So that means that I'm at a relative max. Okay, and so what I'm going to do is I'm going to, now that both of these turn out to be relative extrema, so if f double prime equaled 0, I'd have to go back and use a first derivative test to check the critical values. But here, since they're not equal to 0, I know that I have a relative min at x equals 1, and I have a relative max at x equals negative 3. So my final step is going to be to take these and plug them back in to the original f of x to figure out what the actual relative max and min are. So if I do that, so finally what we're going to do is we're going to plug in the x values that we got for the relative max and min into the original f of x to get the y values. So if we know that we have a relative min at f of 1, then we can say that f of 1 equals 1 cubed plus 3 times 1 squared minus 9 times 1 minus 13. All right, and you can plug that into your calculator and you get f of 1 equals minus 18. Okay, so this here, the y value, is what we're in this case going to say is the relative min. So it's important to remember that when it asks for the relative min, it's asking for the y value. All right, so then the relative max, we said, is at f of negative 3, x equals negative 3. So I plug negative 3 into the original f of x, and I get minus 3 cubed plus 3 times minus 3 squared minus 9 times minus 3 minus 13. And this is going to end up giving me 14. And so y equals 14, or just 14, is the relative max. Okay, so this is a second derivative test applied to cases where the relative max and min are happening at places where the second derivative is either negative or positive. There's also cases where the second derivative equals 0, and in those cases we'll have to go back to the first derivative test to solve them. So that's what we'll do next.